Ladies and gentlemen, the audience, on behalf of the Albert Einstein Society and the University of Bern, it's my pleasure to welcome you for these lectures. My name is Paul Burkhardt. I am the Vice President of the Albert Einstein Society. And I'm delighted that so many of you have made the way to this event. And these lectures have been jointly organized by the University and the Albert Einstein Society since 2009. The topics are alternating between physics, mathematics, and philosophy. This year, the topic is dedicated to physics, more specifically to laser physics and various applications. And the lectures will take place on 3 successive evenings, and please pay attention. The lecture of tomorrow starts at 5:15. And I'm delighted that we have successfully succeeded in securing the Nobel Prize winner for these lectures today. And Uwe will now present and introduce you more in detail. Thank you.
Yeah, thanks, Paul. It is my great pleasure to welcome you all on behalf of the Faculty of Science and of the Albert Einstein Center for Fundamental Physics here at Bern University. And as Paul just said, we have completed 5 cycles of Einstein Lectures, rotating from physics to mathematics to philosophy. And today we are about to begin the 6th cycle with physics, and it is my tremendous pleasure that Donna Strickland accepted our invitation and will be our 16th Einstein lecturer. She is an expert in laser physics, and laser, as you may know, stands for light amplification by stimulated emission of radiation. And this is actually something that Albert Einstein in the year 1917 understood on theoretical grounds. I don't think he had an idea to build a laser with this, and it actually took until 1960 or so when the first laser was actually constructed. So the birth of the laser falls more or less at the same time as the birth of Donna Strickland. She was born in Canada, in Ontario, and she studied physics engineering at McMaster's University, and then did a PhD in Rochester University. There she worked with Gérard Mourou and was working on laser physics. What she developed was the creation of ultra-short, very intensive laser pulses. These are chirped, amplified laser pulses, and this is a discovery with enormous ranges. It has a lot of important implications in fundamental physics research, but as we'll learn tomorrow, it also has medical applications, for example, in eye surgery. I had lasers in my eye a very long time ago. Also in climate monitoring, which will be the subject of the lecture on Wednesday. So all these things are so important that she was awarded the Nobel Prize in Physics in the year 2018. And I should say, 3 years ago, we had Didier Queloz as our Einstein lecturer. He won the Nobel Prize 1 year after Donna, and he gave great lectures about the discovery of exoplanets. And he was actually the 210th man who won the Nobel Prize. Now, Donna is of a rarer species. She is not of the garden variety type of Nobel laureate that you meet on the street almost on a daily basis. she was actually only the third woman who received the Nobel Prize in Physics, after Marie Curie was honored in 1903 and Maria Goeppert-Mayer, who was a nuclear physicist, in 1963. And then it took until another 55 years until Donna got the Nobel Prize. And in a sense, she opened the door for at least two more women until now who have also been recognized like this. Now, I should say that she is a female physicist, but she is just a fantastic scientist. And that's the reason why we invited you. And we very much look forward to your lectures.
Thank you very much, Yuri, for that very nice introduction. All right, so usually I do give my Nobel talk, and I'm going to mention at the odd time, because I was told that I should have Einstein mentioned at least once during these talks, so he will show up just once. You can find my Nobel talk, it's online, so if I show a few slides, you can always go back and get more details. But I am a short pulse laser person, and so I'm going to talk about just how to make short pulses. As you'll see, there are a lot of people that make pulses even much shorter, and maybe your next physicist can be the 5th female laureate, and she can tell you about that. I think the physics crowd gets it easier than the philosophy and the math, because they don't have Nobel Prize winners to say, oh, that's who we should invite. They have to think a little harder. Okay, so I'm here, I'm going to tell you, but I added this part of the title for making molecular movies because this is the application that hopefully the pulses I'm going to talk about would work for. So I will be describing 3 different ways to make short pulses. One is a little too long for this. The other is much too short for this. And I'm sort of like Goldilocks. I want to be somewhere in the middle. So that's what we're going to talk about. And I am from Waterloo. And let's turn this on so it works. All right. So there are 2 reasons really to make short laser pulses. You already said what I'm known for is making short pulses so it can be very intense. And I'll briefly mention that in this talk. But the main reason, and then long before people tried to make really intense pulses by using short pulses, it was in order to measure something that was too fast just to be seen, okay? And how can we stop the action of something going fast? You need to use shorter and shorter time durations. So way back in the 1800s here, there was this controversy because there was this different kinds of horse racing, and I know nothing about horse racing, but this one kind, some people said that they saw all of the legs come off the ground, and other people said, no, I never see all the legs come off the ground. And of course, just because one person says you can do it doesn't mean you believe them, and so they needed some proof. So Edward Muybridge came up with the way to do it. He set up a series of cameras. He knew the speed the horses ran at, so he would know exactly how much time delay to put between each shutter of each successive camera and take the picture as the horse went by each one of these cameras. And then he had a series of pictures. And when he took all these series of pictures, I believe it's this one up here that showed absolutely all the legs were off at the same time. So he solved this dilemma. So he had the time resolution of 1 millisecond, which seems fast, thousandths of a second. And it certainly is fast enough. Those horses in each picture look like they're standing still. So it is a short enough time to stop the action of a moving horse. But a horse is a pretty heavy thing. And so, they can only move so fast. And so you can stop the action with a millisecond. Edward Muybridge, though, was stuck with a millisecond because he was just trying to use the opening and shutting of the shutters. Well, the opening and the shutting of the shutters is also moving mass. And so that's as fast as he could open the shutter and close the shutter to stop the action. And so we were stuck at 1 millisecond for about 50 years. And then Harold Egerton was the one who figured out, let's take the picture in a dark room and only have the light on for a very short amount of time. And then you stop the action because the only light that comes into your camera can only occur over that short time. And so he came up with the electronic flash, and he could make his optical pulse then as short as 1 microsecond. And so this is stolen from the web, although I believe it's perfectly safe to steal this particular one from the web. I hope so. Don't take pictures otherwise of this one. And so you can see that we have a speeding bullet, and it stopped the action because a microsecond is fast enough to stop the action. Now, the thing about the horse and the bullet, though, is that both of these objects are big enough for us to physically see, big enough to use a regular camera to take the picture, right? It's really just how short was the time the light was there for. So now we're skipping along to what we're trying to do now, and what we want to do is watch molecules. But molecules are so small, we can't see them. So you're going to see that I'm going to draw a cartoon. Now, I did try to explain to you that I had 3 communications experts make the beautiful slides of my Nobel talk, and you only have the professor who has to make her own slides. So just be ready for this, right? Because this is my picture of a molecule, and I'm going to make the move even. But a molecule is smaller than the wavelength of the light that we see, and you cannot image. Okay, you could also ask that Nobel laureate who. But he's a chemist, really. Okay, he's really a physicist, but he won chemistry. You know, how you can get a little bit smaller than that, but you can't actually see the atoms of a molecule. Okay, we're not going to talk about taking an image of that, but what we're trying to do is stop the action, just like the picture shows there, okay? And so we want to stop the action, and to do that, we need a pulse shorter than the motion of these atoms in the molecule. And so, you know, maybe do we want to watch, you know, the asymmetric stretch, okay? This took me a while to figure out, I'm just saying. Or the symmetric stretch, like, oh, see, the stick sticks out, but I couldn't fix that. Okay, so now, spectroscopists who use very long, I should just stop it. Hang on. Okay, we'll just stop that. Spectroscopists will say, what are you short pulse people doing? 30 years ago, I heard this chemist, you know, poo-poo people like me, saying, you know, we, in our high-resolution spectroscopy, have resolution way above how short you can make your pulses. You're wasting your time. And so if we were just doing thermodynamically equalized spectroscopy, he's absolutely right. It was a he. Absolutely right. Okay? So obviously this is not what we're trying to do. We're trying to do something that's transient. We're trying to say if we actually make some kind of transition in a molecule that would be bigger than just these ones, can we watch the energy spread, and how does the energy spread? So that's the goal of the work. So we need a couple of things because, as I said, we can't image the molecule. The atoms are too small to be seen. So all we're really going to try to do is, can we determine the distance between the centers of mass, and at different points in time, can we watch these centers of motion move? And there can be many more of them, so we're watching a bunch of center of mass motion moving. That's the whole goal here, okay? So we need 2 things. We need them faster, and I guess I turned off this too quickly, the one before. You know, large atoms will move on the order of 10 femtoseconds, but if you actually want to see the hydrogen, really light, that's the lightest atom, hydrogen, it's going to oscillate at 2 femtoseconds. A femtosecond is 10 to the minus 15 seconds, or a millionth of a billionth. So yes, a millionth of a billionth of a second. So it's very fast. So you need a very fast pulse to stop that action. But we also need a way to measure what was the center of mass position of the atoms. And for that, we need more than just short pulses. We're going to use something called Coulomb explosion imaging. So let me explain that. All right, so we're going to go back to just 2 atoms because that's enough to explain it. So we're going to have 2 atoms, it can be hydrogen, sitting there, and we're going to bring our short pulse in. It's going to be shorter than it's vibrating so that it stops the action. But it has to do one more thing. It has to actually strip one electron off each atom. Okay? And this is because this is what's going to cause it to explode. But first, I'm going to explain how is it that the short pulse helps us strip the electron off an atom. Okay, so it was Planck back around 1900 that taught us that the energy or power of light cannot continuously drop to zero. There is a minimum energy unit, which is what we call the photon. He also showed us that the energy of one single photon is given by its color, or it's given by its frequency. So the wavelength is the distance between the crests. The frequency is the inverse of that. It's the rate those crests come and hit the detector or your eye. These are the colors we see from red to violet. Red has the longest distance between the crests, which is about 720 nanometers, 0.72 microns, and a micron is a millionth of a meter, or a thousandth of a millimeter. So, okay, that's 0.72. Green is the one that we see the best. That's why now pointers are green, because for the same milliwatt, and this should only be a milliwatt, so it's eye safe. I won't send it your way, but a milliwatt green looks a lot brighter than a milliwatt red. And then the violet is not quite a factor of 2 higher frequency or half this wavelength. So again, you only see 720 when you're young, all right? Us old people have lost it. And you also only see down to about 380 when you're young, but it's not quite a factor of 2. That's all we've got in our eyes. For musical people, an octave is a factor of 2, so we don't even have an octave of light that we see. But anyway, again, energy, if you talk about photon energy, none of us can really feel a photon's worth of energy. And so the analogy, I think always in physics gets used, is gravitational energy, because we experience it every day of our life, okay? You guys all get to climb the Alps. So you know that it takes some energy to do that. And so the higher up you go, the more energy you have to do. And so I show red photons as sort of child size, okay? And I'm showing them picking up an electron, okay? So that's as far as a red photon can pick it up in energy. Green is better, and violet can do almost twice the height of the red photon, okay? But it's not really height, it's electrical energy. But okay, so we got it. Here comes Einstein's picture. I'm right. Okay, so what did Albert Einstein win his Nobel Prize for in particular? You might think it's E equals mc squared. You might think it's one of the relativities. It's not even for figuring out the laser in 1917. It is, in particular, for explaining the photoelectric effect. Now, to explain the photoelectric effect, you do have to use Planck's idea of photon energy. And what is the photoelectric effect? People were shining light on materials and watching the electrons come off. Now, they thought light was a wave, and so they thought you just have to turn up the power and the electrons will fly off with more power. But that didn't happen. When they used red light, the electrons just never came off. Didn't matter how powerful that red light was, just didn't come off. But when they used violet light, the electrons came off. But when they turned up the power, the electron energy that it left with didn't change. It only had more electrons come off. And so it was Albert Einstein who figured this out. Now again, Bohr had already figured out that the electrons stay in these orbits. It's just like the Earth is around the sun, okay? But again, it's hard to see energy in the 3D, and so we draw it as sort of a well, okay? And so that the quantum states that the electrons sit in, I'm just showing one now that the photons are standing on, okay? And then to ionize it, you have to get out of the well. And so the red photons can only lift the electron this high, can't get out of the well, but the violet photon could get it out of the well, okay? So he figured that out. All right, so he figured that out. Now I'm going to go to Maria Goldwyn-Mayer, the second woman to win a Nobel Prize in physics, and rightly said by Yui, she was a nuclear physicist, but she didn't start out as a nuclear physicist. This is the advanced theorists, how they're not stuck to experimental equipment. They can just keep thinking about all kinds of weird things. And so when she was a graduate student, She's the one who asked the question, why are atoms stuck only talking to photons one at a time? Can't the photons absorb the energy of more than one photon simultaneously? She showed us it was true. And so if that's true, she talked about absorption, but it works for ionization. This is now called multiphoton ionization. And indeed, you could have a whole pile of red photons work together to kick the electron out. And so she showed us that in 1930, published the sole author paper in 1931, didn't win a Nobel Prize for that. So she got us started, but we've now seen that when the laser came along. So why did we not see it until the laser came along? Well, in order to see an atom simultaneously absorbing the energy of more than one photon, there has to be more than one photon in that volume in order to be simultaneously absorbed. And so that requires a certain density of photons. And regular light just does not have that density. But when the laser came along, it started to have that density. So the laser has a lot of energy coming out, and then to get the density of photons even bigger than that, we use a lens to focus 2 dimensions and make as small a spot as we can. The smallest spot as you can is 1 wavelength, okay? And then the other dimension is really the pulse duration of the pulse. This is what CPA is all about. And so you try to make the pulse as short as possible, so you've crammed all the photons together, gotten the photon density high enough, and you can have now multiple photons in this volume. And the advantage of doing this for ionization, instead of just using an ultraviolet single photon, which you can do, is that now we can control the power of our laser, bring it down, so that, if you need 4 photons, whichever color you're using, you can turn down the intensity so that it's rare but possible for that to happen, okay? You don't have that control if it's just always 1 photon, because it's, 1 photon. So this is why to do this Coulomb explosion imaging, the short pulses give us 2 advantages. 1, we're going to stop the action, and 2, it lets us ionize precisely 1 electron from each of the atoms. All right, did I just say that? I think I just said that. All right, so now back to why do we want to ionize these 2 charges, or however many charges are in our molecule. And so you have to remember, and hopefully in high school, you all saw the pith ball experiment. And if not, first year university, hopefully, those of you who took some science, see the pith ball experiment. And so what this is, and Coulomb did sort of an experiment like this, not quite, but you could, and so I think you read silk on glass or rubber with fur, and one gives you positive charges and one gives you negative charges. And so if you take the charged rod and you hit your little pith ball, which is a light little foamy kind of ball, and you charge it, you can charge both of them with the same kind, and you see that they go apart. You also see they come together. We don't need to worry about this right now. We're going to do this one. And then we see it that it comes apart, and then it stops. It's held out there. This is the same when you put your hand on one of those static balls and all your hair comes out. It goes out, and you can measure then the tension in the strings and this horizontal tension, and you can calculate, and so this is what Coulomb did for us, is showing that the force between these 2 charges is proportional to charge 1 times charge 2, but inversely proportional to the distance between them, the center of masses of them, squared, okay? And so if you could measure this force, then you know how far apart they are. That's mostly the point, okay? Now, a pith ball, though, because you're doing this in your high school lab, so it's a finite size thing, so you can see it. It's not the size of an atom, because we can see this ball. And so it's at least 1 millimeter. And they're at least sitting a couple of millimeters apart. But atoms inside molecules are sitting a nanometer apart. Okay, so that's 6 orders of magnitude closer together. And it's the same charge 1 and charge 2. And then the force is 1 over the distance squared. So you get 12 orders of magnitude more force between those 2 atoms than you did on the 2 pith balls that moved apart. And this is why it's called Coulomb explosion spectroscopy. Those 2 charges sitting a nanometer apart have no choice. The chemical bond between them is nowhere compared to that force, and poof, off they go, okay? So now we still have to measure what is that explosive energy, though. So how are we going to do that? Again, you guys are just here in the Alps, so I chose skiing. And some of you, I'm sure, are very, Europeans seem to be in very good shape. Some of you may even walk your skis up the Alps, but I don't know. Most of the time, I think you would take a lift. And that's because it takes some energy to go up the hill because you are doing work against the force that is pulling you down. And so the work is the integrated force over distance. If it's a constant force and gravity over that kind of distance it's the force times the distance, okay? And so that's the work. Once you're at the top of the hill, if there happens to be like a cafeteria or a lodge or whatever up there, you can stay as long as you want. You don't give up the work you've done to get there. It just stays there, and so that's what we call the potential energy. Because you know, whenever you feel like it, after lunch or right away, you can ski down that hill and get going faster and faster and faster the further down you go. Now, I don't want you to think so much about skiing down, because presumably you don't just go straight. But so more think about ski jumpers here. And ski jumpers, you know, start pretty high. They keep themselves crouched really low to stop any resistance, air resistance, right? And they just want to start as high up, have less friction, and just go down. And you pick up the kinetic energy that you put into the potential energy. And this is what physics is mostly about. One kind of energy turning into another kind of energy. Potential energy and kinetic energy can go back and forth. So also think about being either skateboarder, I don't know if that's big here, but snowboarding. And then they have the half pipe. I don't do this, so this is about as much as I know. But if you start at the half pipe, then you can go down, pick up your speed, and then go back up. You won't quite get there, okay, because there is friction. That's why they usually sort of jump and get down, and go back. And it just keeps switching from potential energy to kinetic energy, potential energy to kinetic energy, okay? And the potential energy is that integrated force over distance. And so the energy of those two pith balls is Q1, Q2 divided by R. So if you could measure that energy, you know exactly the distance between them. And what we're going to do is measure the kinetic energy, and we know after the explosion, and the kinetic energy has to equal, because it's all done in a vacuum, has to equal the potential energy. And that's how we do our measurement. So we're going to come in, we're going to have our short pulse, we're going to ionize that. Again, this is me doing this, so obviously that's not instantaneous, but that would be instantaneous, and then it would explode, okay? And they wouldn't stop. You would measure the final speed and the direction, okay? So if you measured that they went this way, you would know the molecule was lined up this way. If you measured it going this way, you would know it's lined up. And how fast it was going tells you how close they were. And that's the whole thing, okay? So now here's just a cartoon that I've taken, but this time I got permission from Daniel Strasser. And so he told me just a few weeks ago, he almost got this experiment done. Not this particular one, this is a cartoon. So this is a hypothetical 4-atom molecule. And you're going to hit it with whatever, because you want to make that molecule go into some excited state, okay? And then, after it's in that excited state, you want to probe it. So this pulse will actually be more intense than this one. So for those of you that are physicists here and maybe do pump-probe spectroscopy, this is probe-pump spectroscopy, I guess. This is the intense one, because this is the one that's going to ionize it. So just like the horse racing with a bunch of cameras, you're going to have these two pulses. You'll start with this one ahead of that one, and so it would actually measure it the way it starts. Okay? And then each time you can go a little bit later, a little bit later, a little bit later, and you can map out how they come apart. And then in this example, they just said this came off as a dimer, it flew that way, and the other atoms flew this way, and you can measure that. Okay? So that's the whole goal. And I have a neighbor who is an expert in Coulomb explosion imaging right next to me. So for many years, I've been telling him, just wait, I'm going to get a laser ready for you. He's still waiting. All right, so let me tell you what we're trying to do. So the rest of it is how to get the short pulses, because I've now told you we need short pulses, but they have to be intense. They can't just be little short pulses. They have to be sort of big short pulses. So what does it mean to be a short pulse? The kind of light that I'm showing here is on all the time. So it would be one wavelength, and it would just go on and on and on and on and on forever. But if you bring in a bunch of different wavelengths, and you phase them, and what does that mean? That means that you make all of their peaks at one point in space and time all be right here, and then from there you can see that the ones that have the shortest wavelength are here, the long ones here, and they keep coming further and further apart. And the black is just the addition of these waves, all right? That would be normalized. And so as you come away from here, eventually you have as many above as below, and so that goes to 0. So this is what's known as, for the experts, Fourier transform theory, right? But all waves act like this, okay? This is just wave theory, and I'm going to go through a bit of it so you understand how we're going to use this wave theory to make the kind of short pulses that we want. Now, of course, the light that's here in this room has all of these colors, because if we see white light, it means all the colors that we see from red to violet are hitting our eyes. And so we have all the colors, but they're not phased. Each of these colors are going when they feel like going, okay? And so it's just random. And so there's no phase between any of it. This is just me drawing something random. Don't look to see if it matches. But it would just be random. Now, there would be places where you could just have a short pulse, but it would be random when it comes. So you couldn't be doing pump probe spectroscopy because you would never know when that pulse is coming short, all right? So this is what comes out of just regular light. But now let's talk about having light from lasers that we can control, and we can phase them to be together. And so now what we've drawn here is 10 different frequencies. The fundamental one has a period t, and so the frequency is 1 over t. And then we're just going to have multiples of this frequency. So this is 2 over t, 3 over t, 4 over t, all the way down to 10 over t. Okay? And we're going to add all of these frequencies up. And if you look here, at the peak of this one, they're all peaking, and so you get a peak. But over here, it's a peak at a trough, a peak at a trough, a peak at a trough, and so you'll get a 0. And so this is the pulse train that comes out from having these 10 waves added together. Now let's just add 5 of them. So we've taken out the 2 over t and the 4 over t and all the even ones. This time, if you notice, there's a peak and a peak and a peak, just like before. But this time now, the trough is the trough is the trough is the trough, and so you get peaks coming down. Now, detectors, including the ones in your eye, always don't see the waves, or they see the square, okay? And so there's no such thing as negative, so they would flip up. I'll show you that in a bit. But this says that you have half the waves, but you have twice as many pulses, okay? That may not be obvious, but this is what happens. And so in Fourier transform theory, the longest thing here becomes the shortest thing here. So you have the whole spectrum. The whole spectrum is 10 over t spectrum. And over here, the whole spectrum is 10 over t spectrum, okay? So the pulse duration here and here is identical. It will be 1 over 10t, okay? Because it's 10t. 1 over 10 times t. And so there's always this inverse relationship between frequency and time in Fourier transform theory. All right. But the separation here is this 1 over t, but the separation here is 2 over t. Here the separation from 1 over t is t, and this one has the separation of 1/2 t because it's 2 over t. So it's always the inverse, and if something's big in one frame, it's small in the other frame. All right, just to bring that home, this time we have the same 10 giving us this. This time we again only have 5 waves, but they're every one, and they only go 5. So we're back to having the same number, and they're the same distance apart. But now we only have half the total bandwidth that we have here, and so our pulses are actually twice as long. Okay? So again, it's always the inverse. So this is important to remember. And so just to show, this is what it would look like because, again, we only see the square, so we only see positive pulses. So let's say we take 10 of these, which is what I showed. They were separated in frequency by 1 over t. The 1 over t gives the pulse duration separated by t. The entire bandwidth, this is the biggest thing, gives you how short the shortest thing is, which is the individual pulse duration. The smallest thing is actually the width of this line, and I'm drawing it as infinitesimally small, which we in physics love to have. Never exists, but we always have infinitesimal and we always have infinity. Again, doesn't exist. But anyway, infinitesimally small means that our pulses go on and on and on and on forever. Now, this isn't true because we turn things on and off, so that's never true. And on top of that, there's noise, okay? So the noise would make this not go on forever, and it would give this some width. But the smallest thing here, biggest thing there. All right, so now we're going to talk about the 3 different ways to make these phased pulses. And the first one is something called mode locking of a laser. Again, this type of laser that I'm using to point with is a single color. And also, I mean, you gave us the definition, or at least the acronym of a laser, light amplified by stimulated emitted radiation. So when I teach lasers at home, I always ask, what gives it the coherence? What gives it? And the coherence is how narrow a line width can you have? And of course, people want to say the stimulated emission. So then I ask, what's the difference between a laser diode, a light-emitting diode, and a laser diode, okay? So we have light-emitting diodes. They're all over a down set of lamps. We use light-emitting diodes and a laser diode. And what's the difference? Both of them have stimulated emission happening. But the laser has to have a cavity, okay? And it is the cavity that really gives us the very nice clean beam that we show here, and it gives us these very narrow line widths. So a cavity, in its simplest form, is just 2 mirrors. And on a laser diode, that's what it can be, just coat the 2 surfaces. Actually, the original laser was a ruby rod with just mirrors coated on both sides of the rod. All right, typically we don't use just this, but all right, so there's these 2 mirrors, and then what are the cavity modes? Again, if you've ever played with string, and again, this is one of the standard things that you'll do in high school in science class, is that you make standing waves in your string. Okay, and so the ends of the strings have to be nodes, and the fundamental mode is just a half a wavelength, because it will go up and down, and then reflect and come down and up. And so the fundamental mode, whether it's a wave on a string or an optical wave in a laser cavity, is the 2L, okay? And then every other multiple of that, 2L divided by some integer, can fit into this cavity. And so we have a separation of these wavelengths of 2L. But the frequency then, because the frequency now has the speed of light divided by the wavelength, and so it's C over 2L, and you multiply it by n. And so this delta frequency from mode to mode to mode is C over 2L, and the time will be 2L over C. And the thing I love about optics and lasers is that most of the time when we teach you Fourier transforms, the theorists, I couldn't just keep pointing to you every time I say theorist, okay, just say, because you're the only one I know that's for sure a theorist in the room. The theorists love their math, and they will love the beauty of these things from a mathematical point of view. But from an experimentalist point of view, and especially optics, you get to see this math happening right in front of you, okay? And so here it is. So there will be all of these many modes that are allowed. And so they're separated by the C over 2L. But the way, when we're mode locking our lasers ourselves, the experimentalists, theoretically, we will be told to add up all of these waves and put them in phase, but it's not like we see the waves. It's not like we can say, are they all in phase? So we actually see it in the time domain, not in the frequency domain. And in the time domain, we know that what we're trying to do is make a short pulse, and this short pulse, see, they're all phased here, will travel at the speed of light, hit the mirror, come back, and keep circling back and forth, bounce back and forth, okay? And this one is a little bit grayer than that one because this is our output coupler, and 2 to 10%, maybe 30% of the light comes through this mirror, all right? But then the rest comes back. There would be a gain medium here to get amplified back up, and it would hit the mirror again, and another pulse would go out. And so the distance between these pulses has to be 2L, because the light hit here, went all the way back 1L, came back 2L, and leaked out again. And so the separation is this 2L, and the frequencies are C over 2L. And so the time would be 2L divided by the speed of light, or 2L over C. And so it's just a Fourier transform happening right in front of your eyes. So this is what a mode-locked laser pulse looks like. So at the same time that I was working at CPA in the mid-1980s, Peter Moulton was at MIT Lincoln Labs, and he was coming up with a new type of laser crystal. And actually, my favorite laser book was written by Anthony Sigmund, fabulous laser experimentalist. He unfortunately, in his 1985 paper, wrote that the first laser crystal to laser was ruby, and there would never be another sapphire, which is chromium-doped sapphire, to laser. And he had some reason for it, don't ask me. I don't know whether Peter Moulton took that on as a challenge. He went, I don't think that can be right. And so he came up with, he tried several, but titanium-doped sapphire, and it stands to this day as the broadest gain profile of any laser, so it's used a lot now. So unfortunately, Sigmund, before he passed away, never rewrote his book. But we have a bandwidth of almost 100 terahertz, and before you transform that, it gives you 4.4 femtoseconds. Again, I can tell you, my husband and I are both short pulse laser jocks, and we thought we had job security. Because not only did you have to sort of be intelligent, know what was going on, you had to really tweak. You had to really be very good at tweaking to make these complicated lasers work. And now you can buy turnkey lasers that just operate at 5 femtoseconds. It's kind of annoying. Anyway, they can do it now. So we have short pulses that are almost short enough, but remember, I want single femtosecond if possible. So 5 femtoseconds is the one that's too long. And not only that, you have to amplify it. We don't want a mode-locked pulse. I should know what my next slide is, but I don't. Yeah, okay. So here's the large spectrum you can have, 100 terahertz. Biggest thing here, shortest thing there is the 4 femtoseconds. It's the Gaussian shape that has this 0.4, but don't worry too much about that. Shortest thing here, the separation of the modes is 0.1 gigahertz, and this is 10 nanoseconds, and that's because we have 1.5 meter cavity, and that takes 10 nanoseconds for one round trip. But remember, these narrow lines mean that these pulses go on and on and on forever. And so the energy or the power of the laser has to be divided by these millions of laser pulses. So the energy per pulse is not enough to cause that ionization that I need to have to cause, okay? So we have to amplify it. And if you amplify it, I'm just going to go back one. If you amplify it, so you have this whole big spectrum, and you amplify it in the same material, well, the center of the spectrum gets twice as much gain as these parts, and so it gets narrower and narrower and narrower. And next thing you know, an amplified pulse is 20 femtoseconds. So, I mean, come on. I mean, the molecule is just a blur. So that's not going to work. Now, oops, pass that. On the other hand, the shortest pulses to date are 50 attoseconds. It's made with high-order harmonic generation. This was actually supposed to be my PhD thesis. This is what I was trying to do my high-intensity laser for. I was going to try to do the 9th harmonic, 9 photons of energy climbing up, not ionizing, but giving up the energy as 1 photon with 9 times the energy. Okay, that's harmonic generation. By the time I had gotten my laser to go, this French group, which includes and UDA, had already seen the 31 harmonics. It was like, what was the point of me even trying to do my PhD anymore? And by 1993, she had seen the 97th harmonic, for goodness sakes. Okay, so these look like they're getting closer and closer together because, again, experimentalists can't actually measure frequency. We can only measure wavelength, which is 1 over. And so, but these are equally spaced. And they've been shown to be phased together, and that's how they made 50 attosecond pulses. Not going to explain it, but you can have the 5th woman to win the Nobel Prize in Physics come. There she is. And these 3 people won it in 2023 for attosecond physics. So they have pulses way shorter than what I'm talking about. They're actually trying to measure what is the electrons doing in the molecules and atoms, okay? I'm just trying to see what's happening with the atoms. So now let's go back. Oh, but remember, I don't want pulses all the time. So here's my mode lock one. It's giving this long, forever pulse train. Harmonic generation takes this whole pulse, fills it in, and it's got a bandwidth. So now the smallest thing here is this 100 terahertz, okay? And so the whole pulse train can only be 4 femtoseconds long. The pulses are every other harmonic. They only see odd harmonics. So with 600 terahertz, that gives you 1.7 femtoseconds between the pulses. And this one was 67 attoseconds, but they've now seen 50. All right, and so you can see that now there's just a few pulses, and if you could get this even a little bit wider compared, you would have, less pulses in the train and most of the energy in the one pulse, okay? And they can actually do single pulse attosecond now. So this is more what I want, very few pulses. So I'm going to use Raman scattering. Now Raman scattering, Raman did not have a laser when Raman did that back in the 1920s, and so you can understand the original Raman scattering, although I find it hard to understand classically, so we're going to do it quantum mechanically. But what it is that the laser light comes in, hits this molecule, and it could cause it to vibrate. Let's see how this goes. There it goes. It can cause it to vibrate, which means there's more energy in the molecule, so the energy had to come from somewhere, and it came from the light. Or you could have it rotate. There we go. Or I couldn't make the line rotate too, but it's the best I could do. Or you could do that. And so the light goes out. But it's harder to see classically. I mean, you might think, well, there's so many photons, it's just taking one of them away, right? But the energy is very, very small, and so that doesn't make sense. So it's easier to think about it in a quantum mechanics way. And so here is the ground state. Most of the electronic levels are way up there in the ultraviolet, but the vibrational state, the electron's way up there because the electron's very light, and so it can move very fast, but the vibration cannot. So it's a lower energy, it's down here. So here's your photon coming up. What's the index of refraction from a quantum point of view is that it sits in this what's known as virtual level for a little bit of time and then comes back down. That's how the light gets delayed when it goes through transparent material. If, for some reason, you have population also in this level, and because it's so close to the ground level, heat can cause the electrons to go up there. You then can interact with this one. And so if the molecule is now just sitting in this level, the electron is sitting here, it can release a photon of this less energy and leave the molecule in this excited state, okay? And this is a little bit easier to understand, that the laser light converts the energy into vibrational energy of the molecule and a smaller energy photon called the Stokes photon. When the laser did come along, here's the laser. There's a lot of it. So there's a lot of it generating a lot of this light. If it's generating a lot of this light, you are actually taking a fair amount of population where the electrons are mostly down here, 97% of them down here, and just dumping them up here, and dumping them up here, and dumping them up here. And eventually, you got a fair amount up here. And so then this light goes, well, what the heck? I don't have to just interact with this one. I can interact with this one, go up to a different virtual level, and come all the way down, and this is known as the anti-Stokes. Okay? Now, there is energy conservation. So this photon green plus this photon green energy equals this photon red plus this photon blue. Okay, so, and you can see that. This is minus this much energy, and this is now adding it back up. All right, so that came along. People saw that and went, oh, this is a great way to do an experiment, to look for these levels. Okay, we can look for these levels. We're going to use two different laser colors. This one just stays where it is, and this one is going to be tuned. And as soon as it sees a level, when you've tuned it to a level, and you're looking for them, you're doing the spectroscopy, all of a sudden you're going to see this photon. And this is called CARS, Coherent Anti-Stokes Raman Spectroscopy. So the chemists loved it. Off they went, all kinds of people doing CARS spectroscopy. And so there was a group in Japan that thought, all right, so I'm going to try to tune my other laser. And as they tuned it to the edge of the gain peak, up came a laser light at the gain peak and the one they were trying to get over here. And lo and behold, it just matched a Raman level. And so, a lot of times experimentalists are just trying to determine, are the theorists right? But sometimes experimentalists get to see things nobody was even looking for, nobody even had dreamt of. And so here's this group in Japan thinking they're looking for one blue line, and out comes 40 laser lines. And they had to go, what the heck is going on? And so that's why we had to stop and think, why is this happening? But if you look at it, it's a beautiful set of lines. And so it's now called, or at least one of the groups, and the person, it was a Russian, Leonid Losov, from the Lebedev Institute that got me into this field, and he calls it multi-frequency Raman scattering. Because it popped up in different groups, it's called different things, but this names it. This is from my own lab. I will tell you again, you know, I get to work on just beautiful things. I get to make all these colors of a rainbow, and it's more beautiful than what this picture's showing you. So I'm just going to show you how bad your 3-color cameras are, okay? So compared to the incredible eyes that we have. So we have 3 cones, and the camera people think they're mimicking it, but they're not, okay? Because, and now I realize that I was just lucky because we only wear IR laser goggles, and all of these colors are quite intense. So luckily, none of us got blinded by them. But this is just taken off a piece of paper. Like we go off a prism, all the colors get separated onto a piece of paper. Someone took the picture. But we can look with our eyes and see every color differently. We can't see the infrared, which are the ones that look sort of whitish purple up there. We can't see that. So the camera can see that. But then we see red, and it starts with a deep red and gets red, you know, until it's orangey red, until it's orange, until it's orangey yellow, and we see them all the way down until we can't see the ultraviolet anymore. But every color looks different. It's a beautiful thing to see. I just love working in optics. It's such a beautiful thing. So the 3-color camera, though, really just says it's yellow. It's sort of this lime green, which is not real. This color's not real. Nothing looks like that when you see it with your real eyes, okay? So they have some work to do. Anyway, it's a beautiful thing to see. And we see about 16 of these colors come out. So what is it? It is not like harmonic generation. At first, I thought it sort of had the same kind of spectral things, but it's not. And I'm not going to explain that to you. Do get Anne Lullier to come. And so here it is. Here's the one that we saw. We have one color here. This time, we know where the Raman frequency is. So we make our second color be exactly here. And they're both strong now. And so we can have 50% population in both of them. So we can make really strong blue. And that blue can go and make the next one. And this is really strong, and on and on and on it goes. And it's sort of a sequential process, but it's always this 3rd order nonlinearity, 1, 2, 3, making this one. And you know it's sequential because we do it in a hollow fiber, and the infrared comes in here. Now again, this looks like it's red turning yellow, but that's because the camera can see, silicon can see everything above up to 900, and we can only see to 720. And so again, if you were in my lab watching it, you would see it come in, you would see it turn red, and then you would see it actually just become, the last half just looks like white light coming out. And so we actually just watch the light gradually become white. So we know it's a sequential process. And so can it be made short? So a different Japanese group, you know, saw a bunch of lines. And so they put in, so notice they're using 10 nanosecond long pulses. So their pulse train is going to be 10 nanoseconds long. It comes out, but there is something called dispersion. All the colors do not travel the same speed, okay? They all start together, but then they all travel different speeds. And because every color travels a different speed, when they come out, they are not all phased to be together. There is an absolute known phase, but they are together. And so they knew what the phase was, and this is just showing you how much ahead or behind it is where the peak should be. But they just very simply used 3 different kinds of glass or crystals. They angled it so it was a certain length, and they were able to take out this phase difference and make it almost flat, right? So they're almost all phased together, best they could. And look at that. They actually got, we called it attoseconds as soon as it's sub-femtosecond, okay? I mean, you might want to call that a 1 femtosecond pulse, but let's not. And they're separated by 8 femtoseconds. But again, this is a pulse train that's going to go on for 10 nanoseconds. So there's 1 million of these pulses. So the energy is not that great. But the process is right, but the energy is not that great. So we don't want to use 10 nanosecond pulses. So again, this would be that was adiabatic, meaning slow moving, and we're going to do transient, meaning faster. So they had these very narrow line width, because 10 nanoseconds is very narrow. We're going to have shorter pulses, so bigger frequencies. And so theirs went on forever. We're going to try our best to have something that looked like this, so there's a lot of energy in the center one. Okay, that's the goal. Okay, so how did I even get into this? When I moved to Waterloo, I have to say, I had followed my husband to New Jersey because he was at Bell Labs, and he thought he'd died and gone to heaven. And then Bell Labs didn't stay heaven. And so we started looking for jobs, and I'm the one who got the faculty job. And if you left Bell Labs, you were allowed to take your equipment. But since he followed me, he was stuck taking an industry job. So I got his equipment. Now, yeah, I got it all. Anyway, so this was something he had developed at Bell Labs. And so he had a 2-color Ti-Sapphire oscillator. So instead of trying to make really short pulses with all the bandwidth, he had 2 colors that were 100 femtoseconds, and you could tune the 2 colors back and forth. And so I thought, well, what would I do with that? I would CPA it. So that's what I did. And so I built my CPA amplifier, which I'm not going to explain, but you stretch the pulse, you already did that, and you amplify them, and then you compress the 2 colors. So the point was, we had 2 colors, they could both be compressed, and we could tune the 2 colors. I think that's what the next one shows. So the top one is what the oscillator can do, and the bottom one shows that we can more or less amplify what the oscillator does. So we could pick and choose where we wanted the 2 colors. So Leonid Losev, when we published this, saw this and went, this is the perfect thing for my multi-frequency Raman generation theory. Can I come and use your laser? And I went, I love when people want to come and use my laser. Please come and use my laser. And so the first one did not work so well. So let's not talk about it. But then he said, let's do it in sulfur hexafluoride, and we'll use this long hollow fiber, because it's a sequential process. So we have to keep the light focused down so it's intense, and then keep it that intensity. Just so you know, like a regular fiber that's used for communications uses total internal reflection. A hollow fiber does not work that way. It works the same as if you try to skip stones on a pond, okay? So the light just barely skims across and stays in the fiber that way, because you very shallowly focus and it stays in. So we would have, at the beginning, a meter. Most of our work has been done with a half a meter. We use sulfur hexafluoride because the vibration we're going to do is that's a sulfur in the center, 6 fluorides around. There's a breathing mode where all 6 go out and in, out and in. And so we don't have to worry about rotations because it's symmetric, and it's away from all the other Raman modes. So it's a very good one because we're not trying to study the Raman, we're trying to use it, okay? So that was fine. Yeah. This was not one of our best colors, but it matched this PowerPoint. All right, so the very first thing we did then, of course, was just let's turn up the power, because it's a nonlinear thing. It should work better and better and better. And it did. We got more and more and more. And even better, and Leonid Losev had expected this, that actually the long wavelengths, going longer and longer wavelengths, more and more Stokes, did not change much, but we got more and more anti-Stokes, which is good because I'm trying to make single femtosecond pulses. And so the wavelength, the central wavelength should be no more than a single femtosecond. And so we're only going to use these colors and have this be our center wavelength. I was so excited when I saw this. I went, great, and I bought all of the prisms and everything to time these up and line them up, and we thought we were going to have this for my neighbor, I don't know, this is like 2010 or something, a while ago. But then, we turned it up some more, and this happened. So it stops, and most of the multi-frequency Raman generation always gets to about twice where you start. I'm not sure I totally understand that. But then this sort of continuum showed up, and so then we thought, okay, our pulses are too short, there's a competing nonlinearity that's causing this bandwidth. So now we're going to chirp our 2 pulses, and that's okay, and have longer pulses. Also then, I said to my master's student at the time, okay, you've done that. For your master's, you should also change the pressure in the cell so that that changes this phase matching, just so we see what happens with that, or just what the pressure changes. And so he did that. And so before he did a whole pressure range, he thought, I'm just going to do a quick and dirty experiment. I'm going to start, now it's a smaller fiber, So we have more negative dispersion. I can explain that later, but it doesn't matter so much. And now we're using chirped pulses, so both pulses are longer. They have the bandwidth, but they're now longer. And you can see we have no continuum under our 2 pumps. This is the maximum intensity, the maximum pressure we could do. And he halved the intensity, and we got less, which is what we thought. But when he halved the pressure, it was totally crazy. He left this lovely phone message. You're all too young. Most of you are too young to know that we used to have actual phones, and they had answering machines with them. And we left 3 messages for the longest time. Our own 2 kids sending cute messages about why they were late coming home. And this one from my grad student going, Donna, you should be here. I was on a camping trip. You should be here. You should see this. This is so exciting. It's glowing green. It wasn't glowing white because the green colors here were now almost as intense as the 2 pumps. Okay, that was cool. We haven't figured that one out yet. We haven't looked either. But this was weird. It was like there was a continuum not under the 2 strong pumps. When we lowered the pressure, it seemed to move out here. We seem to have this, eating into the continuum on the blue side and these red shifted shoulders on the other. This is why we still have not got short pulses, because since then, a not very good student said, Donna, I think we should study this. And I went, you're right. What is this? And we have looked. This is the end of my talk, so I'm not going to explain it to you. But other people saw it. Other people saw these red-shifted shoulders, and nobody talked about it. Because, of course, the name of the game is to get the most orders, so you get the shortest pulse. That is the name of the game. I'm not always good at playing the game. I thought, this is worth studying. And so we think we have just now figured it out. But we have a little shaky data. So we're waiting to get our new laser systems built and have hopefully better data. But the advantage if it works, you'll see, again, this is on a log scale. So if you didn't plot it on a log scale, you would see much just wider peaks. And remember, if I'm trying to make as few pulses in my pulse trainer as possible, I need those to be as wide as possible. So we're thinking, oh, that would be so great if that works, because now I'll just be almost single pulse, and the pulses will be short, and everything will be great. Now we're pretty sure that's not going to happen because we're pretty sure that we have 2 pulses there, and one has a very wonky chirp, and we don't know how to unwonk yet. So it could be also a problem. But in the meantime, I've got a theorist now working with me on it, and we're going to figure it out. But that's why I haven't made my single femtosecond pulses yet. But I'm close, and I know how to sort of take this away, and I think we could still make the single femto. So I now have 2 PhD students on it. One will keep working on this, and one's going to make the single femtosecond. And I think that's where I'm ending. These are all the people that have helped me do it. Thank you very much.